Hello, my name is Mario Bencomo. I'm a new faculty assistant professor in the Department of Mathematics at Fresno State. And today I'll be talking about topics in inverse problems. Now, this talk is meant to be a very accessible talk to inverse problems. So I'll discuss a bit of introduction on specifically definitions of what inverse problems are. And then I'll focus on some of the challenges, what makes these inverse problems particularly difficult, and I would say interesting. That would be the challenges of ill-posedness and ill conditioning. And from there, we'll discuss a framework for solving these problems, and in particular, the strategy of regularization. From there, I'll jump into some of my research interests, which include large-scale ill-conditioned problems, and the case where the forward problem is a differential equation, resulting in differential equation constraint optimization. So to start off, what is an inverse problem? Well, the definition really depends on what is the forward problem. So the forward problem, think of in general, you're given a function, a black box f, that takes an input x, and it's also dependent on some model parameters m. And you're interested in computing this and figuring out what the output is. So this would be a very abstract forward problem. Again, the inputs are x. The modeling function f could also be dependent on other model parameters, which we denote by m. And the goal would be to compute the output given these inputs. So the inverse problem, having that forward problem defined, can be thought of into two different categories. So you have a causation inverse problem. In that case, you're interested in figuring out what the input was given the measured output. So what would be x if you could only observe from the black box the output y? The model identification problem is that of the problem of trying to estimate the model parameters m. So knowing what the input is and having observed the output, can you say what the model parameter m is? So consider the following example. This is a simple radioactive decay example. In this case, you model the radioactive decay as an initial value problem. So the number of atoms y satisfies this very simple differential equation in which the rate of change of the number of atoms is negatively proportional to the number of atoms at the current time t. And so in this context, the input would be the initial condition. What is the initial number of atoms in your problem? And m, the model parameter, would be the decay constant m that shows up there in the ordinary differential equation. And the output would be the number of atoms measured at time t. So given the simplicity of this problem, you can actually solve the forward problem. The forward problem would consist of solving the differential equation, which would be of this form here. And the causal problem would be the problem of solving for the initial condition x, having observed y at some later time, capital T. The model identification problem can also be solved explicitly, and it's given by this formula here, which is basically we solve for m, having the initial condition x and having the measured number of atoms y at some later time, capital T. So that was a rather simple inverse problem that had explicit analytical solutions to all of the different inverse problems associated with it. Let's look into this cartoon example of inverse problems that highlight the challenges associated with these inverse problems. So consider the following example from Who's That Pokemon? So the goal here would be to identify, based on the shadow, identify what the Pokemon is, right? So this is a causation problem. So we put it in the terminology of inverse problems. We want to know the input, that is the Pokemon. The process here is the process of generating the shadow. and the output would be the observed shadow. So what would be the Pokemon in this case? Well, it's no one else than our friend Pikachu. Let's look at another example. So who would be this Pokemon? Well, if you're a child of the 80s or the 90s, you would be familiar and you would probably say this is Bulbasaur, right? But here we have Pikachu again. So this here, it's a bit of a cartoon example, but again, it really highlights nicely the issue of ill-posedness. So by ill-posedness, we mean that the modeling function f is not necessarily invertible. Okay, even though computing the shadows are straightforward, we know how to compute the shadows. That doesn't mean that going from the shadow to figuring out who the Pokemon is a stable process or a process for which there is a unique input, right? If your function f is not invertible, then if a solution exists, it's not necessarily unique. So you lose that uniqueness here. So both Pikachu and Bulbasaur could produce the same shadow. Another challenge of inverse problems is that of ill conditioning. So by that, we mean that if the solution does exist, it may be, suppose that if the solution exists and it is unique, it may be highly sensitive to errors or noise in the observed output / data. So to really drive home this example, I'm going to go through a more technical example, that of deconvolution, which is the inverse of convolution. So convolution is a mathematical operation between two functions. And what it does is that it takes a function k and a function x, and it does this integral operation on it. And the end result is yet another function in t. So in the context of inverse problems, we denote, again, x is gonna be our input. And sometimes we refer to this as the image or the signal. It has a bit of a electrical engineering connotation, since convolutions do show up in a lot of areas of mathematics. So they tend to show up in image and signal processing, it's in statistics, as well as partial differential equations. So K in this context will be our model parameter and is referred to as the convolution kernel. And B will be our output. Usually we've been using Y in the previous examples, but for this example here, we use B, and this will be the output. So sometimes we refer to this as the blurred image or blurred signal from the result of convolving X, our input, with our convolution kernel K. Solving this problem, the forward problem, that is given two functions, what's the convolution of them, can be done in a discrete way. So the discrete approach would be to essentially replace your integral with a finite summation. Now, there's a bit of technicality here in terms of how do you deal with the summation, especially if you have this business of shifting in the kernel. And so this would result in shifting in the index of summation. And you have to be careful how you deal with that, given that the summation will get you basically indices that are out of bounds. So we deal with that through a convention of circular convolution, meaning that the indices sort of wraps around itself, and that lets us know what to do if the indices do go out of bounds. So long story short, we can define a discrete version of convolution, now dealing with two vectors. So the convolution between a vector k and a vector x can actually be expressed as matrix vector multiplication. Now this is a result of the fact that a convolution is a linear process, and if you're taking a course in linear algebra, a linear process can always be written as a matrix vector multiplication, well, of course, with the appropriate matrix A. So in this example for convolution, the matrix A has the following components. So the ij component is associated with the kernel k at a particular index. And so just to give you a specific example of this, when n is equal to 3, and so your convolution kernel has 3 components, then the convolution matrix A is given as follows. So you see it's got this nice pattern of the K1, K2, K3 repeating in this sort of circular pattern in both in terms of columns and rows as well. All right, so now we have a way of computing or solving the forward problem. And again, the F in our forward modeling in this case is simply matrix vector multiplication by a matrix A that depends, of course, on our convolution kernel K. The inverse problem here is we want to recover the signal X, that is the original input, from observed blurred signal B. So from output B, in other words, we're solving AX equals B. Nothing more than a straightforward linear algebra problem. This again is a causation inverse problem, since we're interested in finding the input. So here's an example of a convolution kernel K on the first plot here, and the resulting convolution matrix A. So here we're looking at in this plot, in the solid black line, the true input, and in B, B is again the observed output without with no noise, so noise-free blurred signal. And we see here in the dashed blue the blurring effects of convolution, which is quite typical. So here's what we get if we were to, for example, if you were in MATLAB, do A\B and compute the input, right? Basically, you're solving AX equals B. So solving that in MATLAB, or just multiplying B by the inverse of A. Okay, so doing that, we obtain back essentially the true results. So everything works out nicely. But of course, this is the case where you have the exact, so noise-free data. And in the real world, that doesn't quite always happen. And so let's look at the case if we were to introduce just a little bit of error. So let B epsilon denote the observed, so the exact or observed noise-free data, now perturbed by the small epsilon, which is meant to denote a small amount of error. And here I'm plotting both the noise-free error and the noisy error. Sorry, the noise-free output and the noisy output. In magenta here, the noisy output, just to show you that it's just a little bit of noise, but that little bit of noise is going to result in basically garbage for your solution. So if we were to again do A inverse B of the noisy data B, the noisy observed data, then we get essentially this high oscillations on the on our solution, our supposed solution X. Okay, so this right here is basically so it shows how sensitive this process is for solving for the input X. So it highlights the ill-conditioned nature of inverse problems. Again, I talked about ill-posedness, or an ill-posed problem, that is F may not be invertible, and ill-conditioned meaning that your process for solving this problem is going to be sensitive to noise. So you want to be smart about how you go about doing that. So the following part of the talk discusses a framework for addressing these problems from the get-go. Okay, and for simplicity, I'm going to focus on the causation inverse problem. That is, we know what the model parameter M is. We have an observed output Y. We want to figure out what X is. So the naive approach was to simply solve this problem F of XM equal to Y. And this could potentially be a linear or nonlinear problem. But as we've seen, right, as we've seen in the previous example, if your F function, so if the problem is ill-posed, then you can't really do this because your F is not going to be invertible. So you can't really solve this explicitly. And if it were to be invertible, it could still be ill-conditioned, resulting in what we just observed in the deconvolution problem, right? And so a first approach would be to take a least squares approach. So rather than solving for x that satisfies this, we're going to find an x that minimizes, in a least square sense, the difference between the forward map at x and the observed output y. And here I'm taking the regular least squares norm, or regular norm here, L2 norm, or 2 norm if you're in a discrete sense. But many work has gone into looking at the effects of using different kinds of norms. How does that change the problem or result in different solutions? But for simplicity, I'm going to focus on simply the 2 norm. So an improvement of this least squares approach would be that the problem is guaranteed to have a solution, at least one solution, which is already an improvement from the naive approach. However, if the problem is ill-posed or ill-conditioned, this problem may still not have a unique solution. Okay, so that's still a problem here. So the next step would be to do a regularized least squares approach. So in this case, you want to find an x that minimizes effectively the least squares objective function that we had in the previous case. And now we have this added term here, mu plus the norm of x squared. Now, the improvement of this formulation is that it can be shown that this problem will have a unique solution. And you could actually prove this doing some SVD, singular value decomposition argument, and you could show this specifically. So that's nice. Let's study this a bit more. So this mu here, I haven't really told you what that mu is, but that mu is referred to as the regularization parameter, and it's taken to be positive. And this mu here really is our way of balancing our goal of minimizing the misfit, right? How well are we close to predicting the observed data y? So how good are we to fitting the data? And so if mu is small, then there's going to be more emphasis into minimizing this term here, the data misfit term. Now, if mu is larger, then the minimization problem is going to focus more on minimizing the norm of x. So we're effectively penalizing large solutions or solutions with large norm, which is what we want to do in some cases. So in the deconvolution problem, right? Now that seemed like something that seemed like probably a good idea. So we'll actually get to we'll actually go back to the deconvolution problem in a moment. So how do you choose mu? So if mu is supposed to be this nice balance between data misfit and penalizing the norm of x, how does one choose it in practice? Well, that again is a very interesting research problem, and there's many heuristics and strategies for choosing them. And I'm going to focus on one of the more fundamental ones, here known as Morozov's discrepancy principle. So let's suppose that my observed data y is noisy, and it is given by the noise-free data y and f plus some error noise epsilon. Okay, so Morozov's discrepancy principle says that you should pick a mu such that the regularized least square solution yields a misfit, that is the norm of the observed data minus the predicted data by the forward map, roughly equal to the norm of the error. Of course, this assumes that you have an estimate for the noise level, that is the norm of epsilon. And so in practice, what this means is that if you know that there's a certain amount of noise in your data, then you shouldn't expect to produce a misfit or a data fit that's better than the noise level. At that point, if you do have a better misfit, then you're effectively fitting the noise, and you don't want to be doing that in practice. And so what's pretty neat about this approach is that you don't need to know epsilon explicitly, but you want to have an estimate of the norm of epsilon, the noise level, which is not an unreasonable thing to have in some applications. So let's turn back to our deconvolution problem and see how we can take this approach for obtaining a more reasonable inverse solution there. So here we're going to use the Morozov's discrepancy principle to pick mu. In this plot, I'm plotting the norm of the misfit. So AX mu here denotes the predicted data given a particular value of mu. X mu is the regularized least square solution. And so AX mu would be the predicted data by that given solution minus the observed noisy data B epsilon. And on the horizontal axis, I'm plotting mu. And so I should also mention that the red line here is where the error is equal to the noise level. So what we want to do is we want to pick a mu that intersects this horizontal red line. And we see this nice monotonic behavior of the error versus mu, which is actually a property that can be proven if you're using the 2 norm for the regularized least squares problem. So that gives us a choice of mu that gets us to the noise level as dictated by Morozov's discrepancy principle. So if we look at this figure here, so this is the result of choosing that optimal mu according to Morozov's discrepancy principle. And this is the true solution in black versus the recovered solution in red. Excuse me. So this is already a large improvement versus the original essentially garbage solution we had through naive deconvolution, right? We're actually able to obtain something reasonable here. But for the sake of completeness, here I'm going to show you what would happen if you chose mu to be too large or too small. Okay, so in blue, you have the case where it's too small. Excuse me, where it's too small. And so what you're doing is if mu is too small, you're focusing more on fitting the data and therefore fitting some of the noise. And that's why you see this high oscillations in your recovered mu x. But if mu is too big, then you're emphasizing your preference to solutions that have a smaller amplitude. And that's why we observed this overly damped solution x mu for mu too big. So you want to have a mu right in the middle, something not too big, not too small. So a research interest of mine is that of large-scale inverse problems. So how do you approach this regularization in the context of large-scale inverse problems? And so what do I mean by large scale? By large scale, I mean that your solution X and your output Y are large vectors. Okay, and so in that sense, it becomes quite expensive to compute the forward map. And store these vectors, let alone solve a least squares problem directly. So most of the time, these problems are solved iteratively by methods that really make use of the fact that these are large-scale problems, and so they try to be efficient in that sense. As we have observed in the previous example, regularization is vital for solving ill-conditioned problems. You need to have a regularization scheme of some sort to address the issues of ill conditioning and ill posedness. Unfortunately, a lot of the common sense schemes, like Morozov's discrepancy principle, is basically so it requires you to compute or solve the problem with different mu's. So in the previous example, we really solved the same inverse problem for different mu's and obtained some sort of result, and then we picked the best one out of the different values of mu. This is not feasible if you have a large-scale problem. You don't have the luxury of solving the same problem multiple times if it's already expensive to solve one time through. And so I'm interested in how do we incorporate these regularization schemes into the iterative methods for solving the problems as it is. So can we, as we're solving the problem iteratively, can we at the same time iteratively determine the regularization parameter as we're doing that? So these are efficient regularization schemes for large-scale problems, and an area of research that is currently being developed in many applications. Another interest of mine is that in which the forward map is not defined explicitly, but defined implicitly through a differential equation. So consider the following implicit forward map. So you have input X and model parameter M, and you would get a output Y, and the output Y is given by the solution of this differential equation, which happens to be the wave equation. So in this context, X plays the role of a right-hand side term or a forcing term, and the M plays the role of the wave speed. And so given the wave speed, given the right-hand side X, then Y would be the solution to this wave equation. So the least squares formulation of this problem would be, given observed data Y, we want to figure out the input X. So we're focusing on a model identification problem. We have the observed data, we have the input X, but we're interested in figuring out what the M is, or the wave speed in this context. So we would solve this. Again, we will solve this through a least squares approach. We have the predicted data. So Ym here is meant to represent a solution to the wave equation given a particular wave speed M. And Y observed would be the observed data. And the Ym has to satisfy this differential equation here. So this is a differential equation constrained, or DFQ constrained optimization problem. So what are these problems pop up in real life, in applications? So here's a particular application that I've worked on in the past. This application is exploration seismology. So exploration seismology is the process, it's the search for essentially deposits of crude oil and natural gas by the recording, processing, and interpretation of artificially induced shock waves in the earth. So just to focus on a particular example here I have a diagram of marine seismic surveying. And in that case, the source that induces the shock waves are air gun arrays. These air gun arrays are canisters of compressed air that, when released, effectively produce an underwater explosion. And this underwater explosion generates acoustic waves that are then met with the earth. And these waves then become elastic waves on the earth. And then you have all this phenomena of refraction, reflection, diffraction. And then later on, essentially the echoes are then measured at receivers at later times. And so the mathematics that I'm interested in is the processing of the data, the processing of this induced seismic waves or echoes. Again, putting all of this in the context of inverse problems, the input in this context would be the seismic source, or these air gun arrays that generate these seismic waves. The the model parameters are going to be the medium parameters. So the wave speed, density, bulk modulus, properties of the earth, of the media, that dictate the differential equation. And the output is going to be the measured seismic activity, or the measured echoes. Again, the forward problem here is, how do we simulate seismic wave propagation? So knowing the source, knowing the input, knowing the model parameters, that is the medium parameters, how do we measure or simulate the data, the seismic waves, as it propagate? The inverse problem is, given seismic data, can we recover information about the earth? Right, so that would be the model identification problem. But if we're interested in the seismic source, that would be the causation problem. Here's an example of a more elaborate mathematical model for modeling seismic waves. This is the elasticity equations, where the source, the seismic source, is modeled by the functions f and g. That would be the inputs in this case. The seismic data would be the vector field v and the tensor field sigma. So the vector field v is the velocity, the particle velocities, and the sigmas are the stress tensor. And in particular, the main diagonal of sigma is the pressure field. So that would be something that could be measured in an actual application. The medium parameters in this case are beta and c. And beta here is the reciprocal of density. So this would be buoyancy, I believe. And c is this tensor. It's a tensor, and effectively it is the generalization of the Hooke's constant. So if you think of one-dimensional springs, this here is the generalization to sort of 3D springs. So that's what the C plays. So this would be model parameters. So I'm going to show you here a demonstration of a solution to this differential equation. And so I should mention that what I'll be showing you is not an analytical solution, but a numerical solution, an approximation to the differential equation, the solution. And the reason why it's we're dealing with numerical is that these problems, especially if you go back and look at the fact that the medium parameters may depend on space, that's already enough of a complexity for this problem to not have a closed form solution. And so in a realistic sense, you cannot solve these by hand. So you have to turn to computers to solve these problems approximately. That's what that's what I'll be showing here. And in particular, the method used for approximating solutions to this problem are that of methods known as finite difference methods. Okay, and particularly, I'm going to be showing a demonstration for 2D. So we won't be looking at the full 3D case, but we'll focus on a two-dimensional example, since it's easier to visualize and look. I should mention that this work here is actually some of the work that I've done back in my graduate school days, specifically at an internship with an oil company, Total, in Houston, Texas. So that was an interesting time for me to explore a potential career path in industry, even though I ended up in academia. So here is the demonstration. Before I hit the play button, what we're looking at here is the vertical axis is depth, and the horizontal axis is horizontal position. So you could think of this as a 2D slice of the Earth. And the top layer here is going to be a water layer. And the bottom layers here is, you could think of it as being the subsurface of the Earth, with an interesting dome-like structure hidden underneath. And so what we'll have is an initial explosion start at the top left corner. And this initial explosion is going to generate acoustic waves that then are going to interact with the Earth and then result in some pretty cool looking seismic waves. All right, so I'm going to pause it again and at this interesting point here. Okay. Yeah, right there. So it's a bit technicolored looking. And the reason why the colors shift around so much is that I was interested in really seeing how the waves were propagating. So I was focusing on demonstrating or showing this in such a way that I could see the full wave as it went by. And so that sort of changed some of the scaling values. So we're able to continue observing the waves, and that's why you see this sort of the colors shift in and out. But here's an interesting thing to observe. Waves that interact with media that have a discontinuity, like in this case, water, the discontinuity between water and earth, result in a reflection and a transmission. Right. And so that's what we observe here in practice in the numerical method. I didn't tell the algorithm to do this. All I did was, hey, here's the PDE. the partial differential equation. Here's a discretization, the finite difference method that approximates the solutions. And then here are the model parameters and the input parameters, the input source to the problem. And so I want to know what the output is. That is here what we're observing is the pressure field as a function of time and space. And so from the differential equation and its approximation, we observe here as a result these reflections, so that bouncing of the wave, and also the refraction or the transmission of the wave that comes through. Now, another thing that's interesting is that we don't see a single wave coming through. We see actually two waves coming through, and we see two waves traveling at different speeds, one traveling faster than the other. And so this is a tall tale sign that you're dealing with elastic waves as opposed to acoustic waves. So seismic waves are the propagation of perturbations in an elastic body. And unlike sound waves or waves in fluids, elastic waves generates not just compressional waves, which is what you're used to in sound waves, but also shear waves. Okay, so both compressional and shear waves. The compressional waves are sometimes known as P waves, P for primary, and the shear waves are sometimes referred to as S waves, or S for secondary. And the reason why they're called P for primary, S for secondary, is that the primary wave travels at a faster wave speed than the secondary wave. And that's always true. And so that's exactly what we observed in the numerical method. And again, that's not something that is inherently cooked up or baked into the simulation. That's something that follows as a result of satisfying approximately the differential equation. So in summary, this presentation, I covered an introduction to inverse problems. Specifically, I went over what a causation inverse problem is versus a model identification problem. And of course, this is relative to the forward problem. Once you define the forward problem, then you can talk about the inverse problem. The two key challenges of inverse problems are ill-posedness and ill-conditioning. Is the forward map, does it have an inverse? In some cases, even if the forward problem is well-defined, the inverse problem may not be. And more than likely, inverse problems tend to suffer from ill conditioning. So the sensitivity of the input relative to noise in the output can be high for these kinds of problems. So you really want to have a framework for solving these problems that addresses these two issues. And usually we do that through regularization. And of particular interest to me are that of inverse problems for which the forward map is a differential equation. And so this would result in a differential equation constrained optimization problem. And so I'm interested in how do I address these issues of ill-posed and ill conditioning specifically for large scale problems. How do we do this in a way that's efficient? And just as important as regularization is understanding the forward problem and solving the forward problem. And specifically in the case where the forward problem involves a differential equation, well, that means you need to know and understand how to solve differential equations. So that in terms of the forward problem, I'm interested in numerical methods for wave propagation problems. How do we solve this wave propagation problem in a way that's accurate and efficient? And inverse problems, again, large scale, ill-conditioned, and accurate and efficient optimization solvers. And thank you very much. I want to thank Lathisms for this opportunity, and you all for sticking around and listening. And I hope to meet any of you someday in person. Thank you.